Good morning. Today I am going to present the paper 2RC model and parameter estimation of lithium ion battery. My co-authors are Mr. Lakshmi Narayana Valluru, Mr. Amol Prakash Khade. Abstract. Electric vehicles are the trends of this decade. Frequent high power requirements of electric vehicles make the batteries discharge at higher C rates. Like whenever the vehicle has to climb at a particular higher slope, then it would expect a higher current to be drawn from the battery. Discharging a battery at higher C rate will lead to higher heat production, leading to destruction and explosion of the battery. To optimize the charging and discharging C rate, considering both safety and the performance factors, battery management system is used as an internal component of power source. To estimate SOC, which is an essential component of BMS, accurate battery modeling is required. State of charge SOC is defined as the ratio of amount of charge present in the battery to its maximum capacity that it can store. 2RC model is one of the most used lithium ion model due to its simplicity and accuracy. The equivalent circuit parameters, resistances and capacitances do change with SOC and temperature. So that is why we need to estimate these values as and when the temperature and SOC change. This paper focuses on estimation of equivalent circuit parameters for a wide range of temperature and SOCs. We have developed 2RC model for battery Panasonic 18650PF and estimated the parameters of model using hybrid pulse power characterization data. MATLAB-based parameter estimator is used in determining the equivalent circuit parameters. From the analysis, it is found that branch resistances R1 and R2 values decrease with the increase in the temperature and a decrease in SOC, whereas the branch capacitances C1 and C2 increase with the increase in temperature and decrease in SOC. Chamber temperatures range from minus 20 degrees Celsius to plus 25 degrees Celsius and SOC range from 100% to 0%. This study will enhance the accuracy of SOC estimation, which is a key feature of any battery management system. One of the challenges in achieving transition from IC engine based technology to electric vehicles is batteries. The conventional lead acid batteries cannot be used in EVs due to their low power to weight and power to size ratio. Due to the following advantages, lithium ion batteries have become first choice for electric vehicle power source, such as high energy density, long lifespan, light in weight, lower self-discharge, and less discharge time. There are two approaches in modeling of lithium-ion batteries. First one, physics-based modeling. Second one, equivalent circuit model. Physics-based modeling is a complex and involved method. This approach employs mathematical formulas based on chemical and physical principles to describe the events that take place inside the battery. Compared to this, equivalent circuit models are simple and robust. Most of the battery management systems use an equivalence circuit model for the of the battery. In equivalent circuit model approach, phenomenal approximation of battery is done using electrical components. The equivalent circuit parameters do not have any direct mapping with the battery chemistry. One equivalent circuit parameter, for example, say R1 alone will not present any chemical process in the battery. But using all equivalent circuit parameters like internal resistance R0, branch resistances R1, R2, branch capacitances C1, C2, will be able to model the complete behavior of given lithium ion battery at a different temperatures and state of charge. Equivalent circuit models use basic electrical circuit components in such a way that it will be able to represent battery voltage for different current stimuli applied to the battery cell. Due to nonlinear relationship between voltage and state of charge of lithium ion batteries, voltage alone cannot be used to calculate the SOC. To reduce the ambiguity about the distance that could be traveled with available charge in the batteries, correct estimation of SOC is needed. To estimate SOC, having parameters of equivalent circuit is very much essential. When SOC is estimated in real time by BMS at any given drive cycle, values of the circuit parameters is needed. The circuit parameters do change with the temperatures and state of charge of the battery, which makes the model complex. Understanding the characteristics of battery with respect to change in SOC and temperature is essential factor for success of battery management system. Very few researchers have published their work in this line and reported the parameter estimation at different SOC and temperatures. Work carried out by Fauzia Khanam estimates values of internal resistances are not for different temperatures and SOC. In the work carried out by Sangum Jan developed expressions for Thevenin equivalent circuit model as a function of SOC, but effect of temperature on equivalent circuit parameters is not analyzed. Since the battery temperature depends on ambient temperature and C rate at which it is discharged, parameters need to be estimated for wide range of temperatures. Work related to impact of temperature and SOC on the equivalent circuit parameter is not significantly reported in the literature. Present work addresses this issue and estimates the parameters for temperatures ranging from -20 to +25 degrees Celsius for SOC changing from 0 to 1. In this method, in this section, information about different state-of-the-art machine circuits and process of parameter estimation is explained. To start with, uh, 2RC equivalent circuit model is developed in the MATLAB Simulink domain. Then we are making use of MATLAB parameter estimation application. Make by using these two things as well, we do require HPPC data in order to provide we require HPPC data in the process of tuning the parameters or estimating the parameters. So these are the three requirements for the parameters to be estimated. That is 2RC model of a particular battery in the MATLAB Simulink domain, parameter estimation toolbox of the MATLAB, and HPPC data set for the particular battery. Okay, the flow chart shown in this particular figure explains the process of parameter estimation. So to start with, so we need to initialize the equivalent circuit parameters. So this is done in the parameter estimation toolbox. The initial equivalent circuit parameters are like in the 2RC model, the branch resistances R1, R2, branch capacitances C1, C2, then the internal resistance R0, then open circuit voltage which is called as OCV. So these are the parameters which we need to initialize. So some initial value need to be given. So after as it is shown next, so these values are used in the 2RC MATLAB model. So wherever we have 2RC model, in that we are using the initialized values as the initial values for those variables. Then what is to be done next is from the HPPC data. So we need to make use of the current input which is to be used as an input to the MATLAB model where we do have a current source as the input. So for which we are required to provide the current input from the HPPC data. Once this current input is provided, so the model is going to determine the terminal voltage. Okay, for the given input as per the equivalent circuit is going to give us the terminal voltage um, whatever it is going to give for a given value of the current input. This terminal voltage is being compared. This terminal voltage, whatever is generated from the model, is compared with the voltage input from the HPPC data. HPPC data also do have the terminal voltage. These two are compared. So it is not expected that in the initial trial itself these two to match. So they will not match, because the initialized values of equivalent circuit parameters are not its actual parameters. So that is why the model terminal voltage will appear different from the voltage input from the HPPC data. If the error is more, so root mean square error is what is being calculated from the error that is calculated in the present iteration, and it is being compared with the threshold value. So the threshold value is taken in the range of 0.02%. Once this value is, if RMSE, the calculated error, if it is greater than the threshold value, then what happens is the values of equivalent circuit parameters like R's and C's gets updated. Okay, so they get updated, and again the iteration gets repeated. Okay, this iteration gets repeated till threshold value becomes uh, greater than the present RMSE value. Once this happens, our estimation process will stop, and the estimated parameters of the resistances, capacitances, open circuit voltage, and the corresponding SOCs get saved in the workspace. So these could be accessed for our use. This is the process involved in the parameter estimation. Okay, so here we can see the equivalent to RC equivalent circuit model. As we can see here, we have a current source, dependent current source, where it is a, yeah, OCV. OCV is a function of SOC. Okay, two RC branches we are having, R1, C1, R2, C2, and R0 stands for the internal resistance of the battery. As the equivalent circuit parameters are functions of state of charge, the range of SOC is 0 to 1. Equivalent circuit parameters need to be broken down depending on the number of charging and discharging cycles performed in HPPC test. To estimate the parameters of lithium-ion battery, it is essential that HPPC test is conducted on the same battery at different charging and discharging rates. After every charging and discharging pulse in HPPC test, relaxation is provided so that the terminal voltage at the end of relaxation period is considered as OCV. In other standard driving cycles like LA92, HWFET, UDDS, etc., the information of OCV cannot be derived, since we cannot have regular relaxations when the battery supplying the load. Hence, we have used, or we are supposed to use HPPC test data for parameter estimation. HPPC test was conducted on brand new Panasonic battery, that is 18650 PF, with a rating of 2.9 ampere hour and 4.2 volt by Dr. Philip Collimer at the University of Wisconsin Medicine, and this data is available open source, which has been used in this particular work for estimating the parameters of that particular battery. The 5 pulse discharge HPPC test was conducted at different C rates such as 0.5C, 1C, 2C, 4C, and 6C for different state of charge levels. From this HPPC test, we made use data with respect to input current impulse, output terminal voltage, temperature, ampere hour, and time stamping. HPPC test conducted from chamber temperatures of 0 degrees Celsius has 54 pulses, and SOC and equivalent circuit parameters have been divided into 55 breakpoints. So that is, all our parameters to be estimated have been divided over their range into 55 points. So that we get the information in 55 breakpoints. The figure shown in the next slide shows the plot of open circuit voltage R0, R1, R2, tau 1, where tau 1 is a multiple of R1 and C2 time constant, tau 2, which is a multiple of R2 and C2 for the SOC varying from 0 to 1 for the chamber temperature of plus 25 degrees Celsius, where tau is multiple of resistance and capacitance. We have estimated the parameters of Panasonic battery of rating 2.9 ampere hour, 4.2 volt using the above approach using HPPC test results available for different chamber temperatures such as minus 20 degrees Celsius, minus 10 degrees Celsius, 0 degrees Celsius, 10 degrees Celsius and 25 degrees Celsius. When the simulation stops, equivalent circuit parameters like SOC, R0, R1, R2, tau 1 and tau 2 are saved in MATLAB workspace. The objective of the work is to understand the effect of temperature on equivalent circuit parameters of the battery. Okay, here is the result that we have obtained. Here the first graph shows the variation of the open circuit voltage OCV, which is shown here as EM, so which is a function of SOC. As we can see, as the SOC is increasing, OCV is also increasing. Okay, then the second figure shows the variation of internal resistance R0 with SOC. The third figure shows the variation of branch resistance, first branch resistance R1 with the SOC. Here, the figures shown are variation of R2 with SOC, variation of tau 1 with SOC, and variation of tau 2 with SOC. Similar plots have been obtained for different temperatures like minus 20 degrees Celsius, minus 10 degrees Celsius, 0 degrees Celsius, 10 degrees Celsius and 25 degrees Celsius. And the data have been obtained as shown in the table. So data we have whatever we have received in the MATLAB and which is stored in the workspace have been abstracted and has been plotted as per the this particular table. Okay, at SOC 100% and how the value of R0 is varying for the different experimentations or different trials that we have conducted for minus 20 degrees Celsius, minus 10 degrees Celsius, 0 degrees Celsius, 10 degrees Celsius and 25 degrees Celsius has been shown in this particular table. Next table 2 shows the variation of R1 for different temperatures and SOC. Here we can note that for a particular temperature, as the SOC is decreasing, the resistance is decreasing. Whereas for a particular SOC, as the temperature is increasing, the resistance is decreasing. Similar is the effect that we can see in R2. But when it comes to the capacitances, as we can see for a particular temperature, as the SOC is decreasing, the capacitance, this is in farads, is increasing. Whereas similarly, for a given SOC, as the temperature is increasing, the capacitance is increasing. Similar is the effect for the capacitance C2, but here we can notice that for a particular SOC with the change in temperature, a large change in the capacitance could be observed. So this is the reason why. So we need to have the values of the capacitances or in general the circuit parameters for all the SOCs and all the temperatures. Okay, in this work, we have estimated two RC equivalent circuit parameters for minus 20, minus 10, 0, 10 and 25 degrees Celsius. In the process, we could analyze the impact of temperature on equivalent circuit parameters for given SOC level. It is observed from the estimation parameters that the resistances of the equivalent circuit are not R1 and R2 decrease with increase in temperature and capacitances C1 and C2 increase with the rise in temperature. This information of equivalent circuit parameters is very crucial in SOC estimation of the battery. The outcome of the work will emphasize the need of equivalent circuit parameters for wide range of temperature. Since some of the parameters, as mentioned in the discussion part, for example, the values of capacitors do even change by the order of 50 times. Non-availability of this information will make SOC estimation poor, and due to its nature, battery becomes unsafe and non-reliable for use. On the other hand, complete battery parameter estimation will make the product globally acceptable, reliable, and safe. So these are the references that have been referred in doing this particular work. Thank you.